And we're back. Welcome back and happy Thursday. Today, we will continue on with our discussion extending on from PLA with more linear models and slightly different variations of linear models. So when we left off, we talked about the anatomy of a learner, and we augmented it with a probability distribution over the input vectors in order to connect our examination of the feasibility of learning with the learning problem itself. We arrived upon the multiple hypothesis case of Hoeffding's inequality using the union bound, and this gave us a new expression for learning feasibility that looked at and included the notion of complexity of the hypothesis set. And from that, we saw that not only must you strike a balance between the error tolerance epsilon and the size of the sample set or training set, you must also balance that against the size or complexity, as it were, of the hypothesis set. So let's continue on and let's look at inputs a little bit and input representation, specifically features. And so the data set I'm going to talk about is the MNIST data set. And NIST stands for National Institute for Standards and Technology. And one of the things they handle is the system that scans postal mail for zip codes. And so here in the figure, we have 16 by 16 binary images or grayscale images of handwritten digits that you might see for zip codes written on a letter. And so as you can see, there are variations of the same letter. So for example, a 5 here is still a 5, but it doesn't look like a 5 here, and the 5 here is a little bit different, but roughly the same types of features as the 5 up above. Now, if we look at these images, they're grayscale, and these images are 16 pixels wide and 16 pixels tall, for a total of 256 pixels. And each pixel can take on a value, and that value represents the gray level from white, all zeros, to black, 255. And so these images are 16 by 16 for a total of 256 values. And if you were to take the image, 16 by 16, and you unroll or flatten this matrix by taking, imagine that first row, and you lay it out, and then you take the second row, and then you concatenate that, take the third row, and so forth, up to and including the 16th row, you're going to get a vector of rank 256. So you're going to have 256 numbers representing the content of a single digit image. And so in its raw form, we can take this input feature vector, this 256 vector, and we augment it with dummy variable x0, as we had discussed with Perceptron Learning Algorithm. And we can also build a linear model for it from before by taking a weight vector, W1 through W256, and augment that as well with W0, which the purpose was to absorb the threshold negative t. And this becomes our model that we're going to use or can use to learn a classifier that's going to classify or predict the labels associated with the output of the ground truth target function for these digit images. So you have some images, and you have images for the 0 digit on through the 9 digit. And the idea then is to build a classifier that will tell you, a learner, is it the 0 digit, yes or no? 1 means yes, -1 means no. Is it a 1 digit? Is it 2 digit? Up to and including, is it a 9 digit? And so this gives us, for our model, a 257 dimensional vector, both for our augmented input feature vector in 256 dimensions, as well as our augmented weight vector, now in originally in 256 dimensions. And so when we look at this, there's some variation, and the full information in the image content might not be useful. So we can study the problem and compute high-level descriptors or features which represent something about the difference between the various digits, but not carrying necessarily the full information. And so one of the things they talk about in the book is using two features, one for intensity and one for symmetry. Now, if we can do this, let's call our intensity feature the x1 feature and the symmetry feature the x2 feature. We augment it and we can come up with a representation such that when we're learning a classifier or building a learner for it, we have a 3-vector augmented, and we have an augmented 3-vector for our weight vector. And so that's very desirable. And so what are we going to do to represent symmetry? Well, for symmetry, we can take our image and we flip it about the center axis, about the vertical axis, and then we take the difference between the representation of the original version and the representation of the flipped version, and then we take those flipped differences and we add them up and compute the negative so that those that are less symmetric will be more negative, and those that are more symmetric will be less negative, closer to 0. And so this is one method we can use for calculating the symmetry, which will boil down the symmetry about the center vertical axis for each digit image down to a single scalar value. Now for intensity, what we can do is add up all the pixel values and take the average. And so those digit images that occupy more pixels in their representation, like this one, it's very thick, that will add up to a higher intensity, further away on average from a value of 0. And so in doing so, we call x1 feature the intensity axis, and we call x2 feature the symmetry axis. And so if we take a look at that and register these points in two-dimensional feature space by their x1, x2 feature, intensity, and symmetry measurements, we can see along this horizontal axis, if that's our intensity, we see that as you go more and more to the right, we have thicker digit images. And so, for example, this 5 over here, it's more to the right than this 5 up here. And you'll notice the 5 down below, which looks like a partial 5, it's thicker, occupies more pixels. The average intensity is higher. Likewise, if we go up, we get more and more symmetric. And so here, if you see this one instance, this blue circle, if we go up, we see that this one is less symmetric. And you see this one over here, the top one, that's higher up, it is more symmetric. And so as you go to the right, it's more higher intensity. And as you go up, that's increased symmetry, more symmetric. And so with this point cloud, we have the red points are the 5 digits, and we have the blue points, the blue circles, those are the 1 digits. Now certainly you can have a 5 digit that's an outlier. Here's a 5 digit that looks like just the top of the 5. It's mixed or mingled in this part of feature space where you see a lot of 1 digit representations. And so we have 2 point clouds. We have the blue and we have the red. The red X's are the 5 digits, and the blue circles, those are the 1 digits. And so the idea then is to build a learner that can distinguish, in this case, the 1s from the 5s. And so you only need pairs because you only need to know the positive examples versus the negative examples. And you can do this with a linear function. So let's take a look at linear classifier. Now, to jog your memory, we said the linear classifier is a weighted sum. So you take your weight vector, multiply by your input vector x, and we treat this threshold, negative t, as a constant, w naught, in the beginning, we use that W naught variable to absorb that minus t. We add in our dummy variable x naught, whose value is fixed to 1, and we rewrite our summation expression as the sum for I goes from 0 to d of wi xi. And we said we can rewrite that in vector matrix form as the inner product between our augmented w vector and our augmented x vector, where augmented w vector consisted of the augmentation w naught along with w1 through wd, our d-dimensional weight vector, our linear model, and our augmented x vector consists of x naught, our augmentation, along with our original x1 feature up through xd feature. So we have our augmentation, our dummy variable x naught fixed to 1, and we have that along with our original x vector in feature space from R super D, d-dimensional real valued space. And so in vector form and closed form, our hypothesis for a specific instantiation or working hypothesis is just the sign of the inner product between our W vector augmented and our augmented X vector. So sign W transpose X. And so we said the algorithm for searching is we're given a training set. That's our historical data, and these are label instance pairs. So for each d-dimensional vector, we have the ground truth label assigned by our unknown target function f. And so we start out selecting our misclassified example, and we use the PLA update rule, which says the new version of augmented vector W is the old version W plus yi, the ground truth label, xi, which is the augmented misclassified input. And so we demonstrated last time why this works. It corrects for an error relative to a misclassified error and updates the weight vector. Now, of course, we could have a learning rate, and this learning rate, eta, would shunt off the action of this update to make it less aggressive. Okay, so let's recall the Perceptron Learning Algorithm, and this was done as an experiment by the author of the main text, and we have our working hypothesis parameterized by a specific instantiation of the weight vector, and we select a misclassified example where the hypothesis disagrees with the ground truth target function, and we produce an update based on that particular misclassified instance. So if we do this over a number of rounds, 1,000 rounds, the purple line, that's out of sample error, E out, and the green line is in sample error. Now you might ask, how do you produce out of sample error? Well, you take your training set, you set aside some percentage of it, and then you use the remaining part of your set, you train on it, and then when you get your final best hypothesis, you bring back out that part of the data set you set aside, and then you run your final best hypothesis on it, pretending as if that set aside data were new data. That is an estimate for out of sample error. And so the purple line was produced that way, and one thing you'll notice here, that E in tracks with E out. And so you see E out starts out as high, E in starts as high. Then with the first few rounds of training, E in drops and E out drops the same amount. And you notice here, they're tracking with one another. E out and E in are some distance apart from one another. So when E in goes up, E out goes up. E in goes further down again later, E out goes down again later. E in stays the same over some number of epochs of training. E out stays the same. E in goes up, E out goes up. So they track with one another. That's just a nod towards Hoeffding's inequality really is a thing, right? E in and E out are within some epsilon of one another. And so here you notice that some cases E in gets better and E out gets better, improves, lower is better, less error. Other times it increases. And that increase is due to when you correct for a misclassified example, you might be damaging an already correctly classified example. And so we see after a number of rounds, 1,000 many rounds, we see that it halts and we have an expression for E in and E out. Now, when we train this way, after 1,000 rounds, you get something that looks like this from that same representation of the 1-digit versus 5-digit using a randomized initialization. The final best hypothesis for this perceptron learning algorithm is this black line. And so you'll see, okay, it does a decent job, but these points, blue, are misclassified, and this red, of course, is misclassified. Now, one of the things you'll observe is that there's some interspersing of these red X's, our 5 digits, with the blue circles, our 1 digits. This data set, if you look at the geometry, you cannot find a straight line that separates them. It's not linearly separable. And perceptron learning algorithm, it'll do the best it can, but if your problem is not linearly separable, it will not produce a final best hypothesis that completely coincides with the unknown target functions labeling. Okay, and so we can improve upon this. One of the things we can do is something called a pocket version of PLA. And what this pocket PLA does is that it does not allow the perceptron learning algorithm to degrade. It either improves or stays the same. And this only requires a single register, single variable. And let's call this variable W. And this W is the pocket. And how it works is you run PLA for some number of rounds, and you force it to terminate after a fixed number of rounds. So T, or time instant, in this case, is 1,000 rounds. And as you are iterating over your rounds for the PLA update, if the update produces an improvement, the new hypothesis, you replace the pocket weight. You put it in your pocket, you store it in W, set it aside, and if the update does not result in an improvement, in error gets smaller, then you discard it and you keep running PLA. So in that particular case, this in-sample error, it can either get better, decrease, or stay the same, but it rejects the increase. It does not put it in the pocket. And so when we look at the pocket version of PLA, we notice something very interesting happens. So we start out, well, E in starts to drop, E out drops, and you'll notice again, E in and E out track with one another, right? They're within some epsilon. They follow one another. And so as we go, you'll notice here, right around here in the pocket version, when it increases, it rejects that and it only takes the decreases. So right when we get to about this point, let's call that 250, 125, about 100, 110 rounds in our set of iterations, we notice that it drops again, and of course we accept that, we hold on to that weight in the pocket, put it in our pocket, and we continue. Now subsequently, after that point, about 110 iterations, we no longer accept the weight update, we don't put it in our pocket, and we keep that as our final best hypothesis. And yet still we see that E out tracks with E in. When E in drops that last amount, E out also drops with it. It tracks, E in tracks with E out. Okay. And so the interesting thing is this works in the non-linearly separable case, because here we're not accepting those weight updates that result in a degradation in performance. And so this algorithm also has another interesting property. It either improves or stays the same, and that has a name. That quality is called an anytime algorithm. And it's a type of algorithm that either improves in its performance or stays the same as you continue to run it. So it never gets worse, which is very, very nice. And so we go from the original PLA to a much more stable behavior just by the simple addition of this one variable, our pocket, W. Okay, so this just says what seemed like a very simple, very weak, very impoverished method, PLA, with a simple update, we can dramatically improve its characteristic as an anytime algorithm as well as its performance, it gets better and never gets worse over time as you continue training it. We can dramatically improve it just by the addition of a single variable or single register, namely the pocket. And so this is called pocket-PLA, and we can absolutely make a dramatic improvement on PLA's accuracy, performance, as well as stability just by making this one simple addition in the pocket variable. All right, so you keep that best setting, W, in your pocket, and you run PLA, and you have it terminate after a fixed number of iterations, and you replace the pocket weight with your new weight update if you find that new weight can do better, it's better performing. And so this PLA iterates over misclassified points, and because it can damage good solutions, this pocket forces it to only consider better solutions. And so PLA does not converge in general if the data set is non-linearly separable. But with the simple addition of the pocket, you can kind of force it to never get worse. And so in the frame on the left-hand side, we have our data set of the 5 digits, our red points, versus the 1 digits, our blue points, from the perspective of intensity along the horizontal axis and symmetry along the vertical axis. We have this black line, which is our final best hypothesis, G, by the normal or unadulterated PLA weight update. And on the right-hand side, we have the same data set, but this is the result of pocket-PLA. And you'll notice here, pocket-PLA makes far fewer errors for the final best hypothesis, G. You'll notice the only ones that are errors, of course, this red one you can't do much about. That's very interleaved. It's an outlier. But you see here that most of the errors are along or very close to the decision boundary. And so this provides a dramatic improvement for very little extra work, this pocket, as it were. Okay, so let's take a look at linear regression. We talked about classification, and in classification, we called it a so-called binary decision problem. And it's called a binary decision problem because the label set is binary. We have a +1, -1, so our label set is of cardinality too. Now, in linear regression, what makes a regression problem, yes, it's a linear model, but in this case, for regression, the label is real value. And so regression corresponds to a learner that has a label set that are real value. And so if we were relating this back to the credit approval problem, the question that we'd be answering is how much credit do we extend? What's the size of the credit line that we wish to extend to a person versus should we approve him or her for credit or deny him or her credit? And so the input, again, is going to be the set of attributes that collectively describe the credit applicant, and the output is going to be the weighted sum for the augmented feature vector along with the augmented weight vector. But in this case, we just output the result of the inner product W transpose X, or the so-called score, instead of sign W transpose X. Sign W transpose X says yes or no, you're a good risk or a bad risk to extend credit, but the W transpose X answers a different question, a real valued question, what or how much credit should someone be assigned? And so we have, again, historical data from the credit officers from the bank, and we, again, have the description of each one of our customers, X1, X2, X3, up to including Xn, again. And associated with each instance is the label where each one of these Yi are drawn from the set of real numbers. They're each scalars representing the amount of credit. And so what linear regression tries to do is it tries to find a hypothesis, just like in classification, our learner, as we've been talking about prior to this, it tries to replicate the decision criteria, i.e., how do you set the weights so that the scores match the real valued labels. So you're trying to replicate the decision criteria as to the real values associated with each customer, where the real valued quantity, our real valued label, is the amount of credit each person was extended. And so the question then is, how well does W transpose X approximate the ground truth target function? Now in this case, by approximate, this ground truth target function, instead of assigning +1, -1 labels, is going to assign real values to each one of the input feature vectors representing customers. And so here's an example of a one-dimensional feature space representation. Now here on the horizontal axis, we have some feature associated with a customer. And this feature could, for example, be the annual salary. Now along the y-axis, this is our real value associated with that particular customer. And this real value is the amount of credit associated or that was extended by the bank. So for example, let's say this point, the projection along the x-axis, let's say that was $30,000 per year. And then the projection along the y-axis, that might be, for example, $10,000 worth of credit that the bank is willing to assign or extend to that person. So we have our data set, and each data point has an associated ground truth real valued label. And what we're after with regression is the best linear fit. And so we take our regression line, our linear model, and what we're striving to do is minimize the so-called regression loss, the difference between the ground truth real valued label, the amount of credit, and what is predicted by that linear model. And so this linear model here for a specific hypothesis, working hypothesis, is this blue line. And for that data point, well, the blue line assigns the following value. And so for that same data point here, the difference between the ground truth label and what the hypothesis outputs is this straight line projection from the point either down to or up to the regression line. And so what we're after then is to try to minimize this set of distances or differences between the ground truth label, our real valued line of credit, and the predicted label by that hypothesis. Now, we can do this in two dimensions. In 2 dimensions, we might have, for example, along the x1 axis, we might have the salary, and we might have the years in residence as the x2 feature descriptor for each one of the customers. And in that particular case, our linear model is going to be a plane in 3 space, and our ground truth label here is this axis, this z-axis, if you will, going up and down. And if we take each point, we can project that point down to the x1, x2 plane. The projection along the x1 axis, that's our salary. The projection along the x2 axis, that's our years in residence. So that might be $30,000, $30K. This might be, for example, 5 years in residence. And then the projection along the y-axis, that's the amount of credit. That might be our $10,000, 10K. So the same idea occurs in this 2-dimensional feature space representation. It's 2-dimensional features, but when you include the label, that's another axis. And so what we're doing is we're trying to fit a plane. A plane is a linear model in more than 2 dimensions. You call it a line if it's in a 2-dimensional representation. You call it a hyperplane or a plane if it's in 3 dimensions, and it's a hyperplane if it's more than 3 dimensions. And so again, we take each of the points and we measure the difference between the label, real valued, for each point in the plane, and the goal is to find the hyperplane that minimizes the sum of all these differences across your data set. And so the error function we're going to use is called squared error. And it's squared error because we care about the magnitude of the difference, but we don't care about the direction if it's greater than or less than. And so here we're going to produce an expression for our in-sample error. And this in-sample error, we take the difference between the label, so here's our label, it's real valued, and the score for that hypothesis, and we square that difference, and we add them up over each one of our big N many data points from our historical data. We take the average of that. So E in is the average squared error loss, or the average magnitude difference between the hypothesis prediction for that amount of credit for that individual, or the score, and the ground truth real valued label. And so if we look at this, we have the sum, and the sum takes the feature vector, that should be n, for each input customer representation, and we compute W transpose X for each one for that score. And then we subtract off of that the individual label. And so we can cast this in vector matrix notation using something called the design matrix, what the statisticians call the design matrix. And the design matrix is a so-called row matrix, and it's called a row matrix because the rows contain vectors of interest. And so here in this design matrix, we convert each one of our input vectors, and we assume that each xi is going to be a column vector, and the first feature is xi0, xi1, where this is the dummy variable, all the way up to including xid, the d feature. And so if you look at the rank of this, well, that is d plus 1 rows by 1 column. So this is a d plus 1 by 1. Okay. Now, of course, if we take the transpose of that, well, xi transpose is now a row vector. So we have xi0, xi1, up to and including xid. So that's the row vector. And we can abbreviate that or make it more visually pleasing by just writing xi transpose. And so the design matrix, big X, is a matrix formed by taking each one of the augmented feature vectors for each customer and setting its rows to be the transpose of each one of those augmented X vectors. And so here we have X, and we know that the vectors augmented are d plus 1 rank. So we're going to have d plus 1 columns here, and we know we have a data set of size big N, so we're going to have big N many rows. So our design matrix is going to be N by d plus 1. It's going to be the rank. And then for each one of these N many feature vectors, we have a single label. And so the label vector, we'll introduce this notation, Y, is going to have N rows and 1 column. So it's an N by 1. And so we can have the same effect. This W transpose X for each one of these vectors is the same as taking our W vector, and again, W vector is a column vector, so W transpose is going to be a row vector consisting of W naught, W1, dot, 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 up to and including WD. In vector matrix notation, we see that we have each one of these augmented X vectors as a row. And so if we want to produce the W transpose X, that's the same as multiplying your W vector term for term with each one of the augmented X vectors. And so here's my X vector. If I want to multiply X vector times a W vector, I want to multiply each row of my design matrix with the original W matrix. And here's my W matrix. I'm going to write it in there. It's W naught, W1, up to and including WD. And so my W transpose X, of course, that's 1 row by D plus 1 columns. My original W vector is of rank D plus 1 rows by 1 column. And so I take one of the rows here, X vectors, multiply by W. And there's the same result as my W transpose X. So I'd write that in vector matrix notation as XW. So there's this part. And so that takes care of this first term in my summation. And then I subtract my Y vector for each one of these rows. So I subtract the Y1, I subtract the Y2, subtract the Y3. And so that gives me this part of my vector matrix notation. Now, of course, I take the norm rid of the square root part of the norm, and this is my expression for my in-sample error. I multiply by this 1 upon n, and that's taking the average. And so in-sample error, then, is the average squared error loss, that difference between the score, W transpose X for each augmented feature vector, and the ground truth real valued label. All right, so here's my expression for in-sample error, and essentially what I want to do is find the W vector that minimizes in-sample error, because that minimizing W vector is going to correspond to the final best hypothesis. So let's take a look at this. So what I do then is I take the gradient of in-sample error with respect to W, so it's the derivative with respect to W of this in-sample error, and I set that to 0 and then solve for W. So if I look at this, this expression is like saying, let me take XW minus Y, X is my design matrix, and it's like squaring it, right? So this norm, well, that's like taking the square root of something times itself. So I have XW minus Y, which is a vector, and when I take the magnitude, that's like saying XW minus Y times XW minus Y. So that's like saying XW minus Y transpose times XW minus Y. That's how I do the dot product of something with itself. That's the magnitude. And then I have that square root, so I square it to get rid of that square root, and I'm left with XW minus Y transpose XW minus Y. And so that's just the expression of something times itself in vector matrix notation, which is like squaring it. And so if I take the derivative of something squared with respect to that parameter W, essentially what I'm going to do is a U substitution. I'm going to compute the Jacobian. And when I do that, that's like saying, what is the derivative with respect to U of U squared? And so what is that? That's just 2U times du dw, where W is this weight vector, which is what I'm taking the gradient with respect to. And so if I do that, okay, well, I have a 2 times this leading coefficient, 1 upon n. Now, for this U, well, that's XW minus Y. So there's my XW minus Y. And then my du dw, well, du dw is the same as saying d dw of that XW minus Y. Now, Y is a constant, goes away. I have W to the 1 power, and that's just X. And so I have two terms. I have XW minus Y transpose times XW minus Y. So I do this du dw on this first term, and that gives me my X transpose. And so that's my result. I set that equal to 0, and then I solve for W. So now I'm left with this expression. I'm left with 2 upon n, X transpose XW minus Y is equal to 0. Now, the first thing I'm going to do is I'm going to multiply both sides of equality by this n upon 2. So if I multiply n upon 2 on the left-hand side of equality, I multiply everything on the right-hand side of equality by n upon 2. Well, lo and behold, this goes to 0, because 0 times anything is 0, and this cancels. The n's cancel, and the 2's cancel. And I'm left with X transpose XW minus Y is equal to 0. So now I take this expression, and I distribute this left multiply X transpose by this parenthesized expression. And if I do that, that gives me X transpose XW minus X transpose Y is equal to 0. I add X transpose Y to both sides of equality, and that gives me X transpose XW is equal to X transpose Y. And that's my next step in this formulation. So now, if I look at this, I have W on the left-hand side of equality, I want to isolate that W. So what am I going to do? I need to take the inverse of this expression. Can I take the inverse of that expression? Well, let's think about what the design matrix is. We said the design matrix is that matrix where each one of our augmented x vectors, x1 transpose, is one of the rows of my matrix, all of my augmented data points. And we said x is of rank n many rows, because they're n augmented data vectors, by d plus 1, because I have d dimensions for my original feature vectors, and I augment it with x naught, so that's n by d plus 1. So if x is of rank n by d plus 1, x transpose has rank d plus 1 by n. Okay, so if I have x transpose x, well, what's the rank of that? Okay, well, x transpose, that's d plus 1 by n, and I'm multiplying that with n by d plus 1. And so the result, x transpose x, by the rules of linear algebra, is going to be d of rank d plus 1 by d plus 1. So this is going to be of rank d plus 1 by d plus 1. And our w vector, we said, that's a column vector, and that w vector is of rank d plus 1 by 1. And so if I multiply these two together, well, that's just going to be, the result is going to be d plus 1 by 1. But I notice here, this x transpose x, that's d plus 1 by d plus 1. So that means I have d plus 1 rows, and I also have d plus 1 columns. So it's a square matrix. A square matrix is invertible. Inverting of matrix is 1 over the determinant times the matrix of cofactors. And so what I'm going to do then is I'm going to left multiply both sides of equality by x transpose x inverse. So if I do that, I get x transpose x w times x transpose left multiply by x transpose x inverse. And I also left multiply on the right-hand side of equality. That's x transpose x inverse x transpose y. And that's my result. And so the square matrix is invertible, and I get the following result, and this is W. Now, of course, this quantity here has a name. This quantity is called the pseudo-inverse by x transpose x inverse times x transpose. And it's called the pseudo-inverse of x because if I take that pseudo-inverse, x transpose x inverse times x transpose, and if I left multiply that with x, my design matrix, my result is identity. Why is that identity? Because I group this multiplication together. I have x transpose x inverse times x transpose x. That goes to identity. And it's called the pseudo-inverse because left multiply and right multiply don't produce the same result. Hence, pseudo-inverse. And so the pseudo-inverse is my result. Pseudo-inverse times y is my result for W, the final best hypothesis. Now, you might be wondering, well, why do you call this the final best hypothesis? Well, we kind of did learning by mathematical manipulation. In calculating this result, pseudo-inverse, you could actually take your data set and write this expression in a handful of lines of MATLAB, and that is your search, as it were, for the final best hypothesis. You're finding a W by mathematical manipulation. Now, of course, if you look at pseudo-inverse, you can line up all the ranks of all the terms in your pseudo-inverse. We said x transpose x, that's d by 1 by d by 1 in rank. And you said x transpose x inverse, that is just going to be d by d. And you're going to multiply that by x transpose. And x transpose, we said, is d plus 1 by n. So the result of this is going to be d plus 1 by n. And you're going to take that d plus 1 by n, and you're going to multiply it, as we said, by y. So you take something that's d plus 1 by n, And your y vector, we said it's a column vector, and that y vector is column vector, and it had y1 through yn, and that is of rank n rows by one column. So we have d plus 1 by n, and we multiply that by an n by 1. Our result, which is our vector w, this result has rank of d plus 1 by 1. And of course, our w vector, lo and behold, as we said, is a column vector, right, consisting of w naught through wd. Guess what? That is d plus 1 by 1. And so the ranks all work out, and we use the pseudo-inverse to find the regression solution for the final best hypothesis, w, for the best predicted real-valued labels. And this is the regression problem. And so the linear regression algorithm takes as input your data set, you augment your data set, you augment your w, add the w naught or include the w naught, and you have your vector of ground truth class labels, the real values from your data set, and you construct your design matrix from the input data by augmenting all the d-dimensional feature vectors. You construct your target vector, and you just compute the pseudo-inverse and return back w as the pseudo-inverse times your target vector, and that's it. So you can use linear regression outputs. They are real valued functions. And so what you're doing with regression is predicting real valued outputs. You find a learner that most closely agrees with the ground truth target function in its assignment of real values to input data. And so when we talked about the binary decision problem for classification, well, binary functions, we said +1, -1 for positive example minus negative example, those are certainly real values. So you can actually use a regression solution to try to approximate this assignment of +1, -1 by binary labels to training inputs. And in doing so, you can use linear regression as a bootstrap or starting place for binary classification. So you can try to use sine w transpose x to agree with +1, -1, which is what we did with the PLA update. But a good initial setting for your weight vector that you can do quite cheaply in closed form using the pseudo-inverse times the target vector is to use regression and then continue on with PLA from a bootstrap of the regression weight vector solution. Now remember, PLA can be very slow to converge because it's going painstakingly, step by step by step, through each one of the misclassified training vectors. And so you can speed up PLA by starting with the regression solution. And so if we do this for the same problem, the binary digit classification, 1 versus 1, so the 5-digit versus the 1-digit, again, the intensity axis was the horizontal axis, the symmetry axis is the vertical axis, the red points are the 5 digits, and the blue circles, the blue points, are the 1 digits. And so using that bootstrap PLA, you can speed up the performance of the algorithm, i.e. by lessening the amount of time it takes to run PLA by bootstrapping a starting place for the weight vector, the initial hypothesis, using the regression solution. And so with that, you get the following solution, and it does a pretty decent job. And you throw in pocket-PLA, and you have a fairly good system. So yet again, we have this very simple linear model, PLA. We add a pocket. It becomes an anytime algorithm. It improves but never gets worse. We bootstrap it from the regression solution, which we can do very quickly in polynomial time. And here it is. We can have a much better system just by making these very simple modifications. So let's take a look at nonlinear transformations, and we'll end with this. So the data in the world is not always linear. Suppose we have the following arrangement. We have some data points belonging to two categories. The blue category projected onto feature 1 and feature 2 are more in the middle. And so the center of this feature space representation, if we were to draw origin, the origin would be right in the middle. So let's assume that the geometry of this feature space was such that the blue points tended to be closer to the center and the red points tended to be further away from the center being the origin in feature space. Now, if we wanted a hypothesis that's going to separate the blue points from the red points, i.e. coincide with the ground truth target function, we can't find a line that does that. The best hypothesis that does that is going to be an ellipse, but a line is not an ellipse. So what can we do? We can rearrange the geometry through some transformation. And so the world is not always linear. We could have credit line affected by years in the home, and that's a measurement of stability. And maybe if years in the home is less than 1, it affects you. If it's greater than 5, it does not affect you. It really matters between 1 and 5, but maybe after 5 years in the home, it doesn't really have much effect. And so with a regression solution, we said that we take the score, which is just the weighted sum of the augmented weight vector and the augmented feature vector. And for classification, we take sine of W transpose X. In this case, the inputs are constants, and it's linear in the weights. It's a linear model. And so for this linear model, it's linear because of the weights. Each one of our input feature vectors is considered a constant in this model. And so as it's just another constant, we can absolutely compute some transformation on the feature vectors. And in doing so, we can transform or change or alter the geometry of the feature space. And so let's go back to this example that we gave where the blue points tend to be closer to the origin in feature space and the red points tend to be further away. Well, with a polar transformation, we transform each of these data points. So we take first feature and second feature for each point, and we square the first feature, square the second feature. This polar transform, the so-called phi function, is any function that you compute over the original unadulterated feature space representation to produce a new one. And so for every point in the original representation, we have the corresponding point where the new features are the squares of the original features. And in doing so, you see that we change the geometry of the feature space. And so in this case, in the original representation, these are not linearly separable. We can't find a linear model that will separate the blue points from the red points, thus coinciding with the ground truth target function. But when we make that polar transformation, we see that points that are closer along the horizontal axis radially tend to be closer to origin in the new representation. So that's the blue points. Also, points that are closer along the second feature axis tend to be further down in the representation. So here we see the blue points that tend to be closer to the lower left-hand corner in the new representation. Likewise, you see those points that were further away from the origin in the original representation, because they are radially further out, both along the first feature axis and the second feature axis, they'll tend to be further away, more higher up and to the right in the new representation. So now, in this new transformed representation, now we can use a linear model because these points are linearly separable. And you see here a straight line like this will separate them. So the interesting part about this is that we haven't changed the model. It's a linear model, but it's linear in this transform space. And because this is a nonlinear transformation, you get the same effect as if you were using a nonlinear model, as if you were using this ellipse. And so here it is, again, once more. We have a simple linear model with a simple update rule, and we saw that the geometry of the feature space was such that it was not linearly separable. But using the same PLA, we perform this phi function, which we can do quite easily in polynomial time, to transform the geometry of the space so that it is linearly separable. So now, then we could do a regression bootstrap using pseudo-inverse times the target vectors, and then we run pocket-PLA, and we are guaranteed that we're going to converge to the optimal final best hypothesis that perfectly coincides with the ground truth target function. And so this is just to show you that you can take the same learner and by making very small adjustments, take a very simple model, very weak, impoverished model, and get it to do powerful things. And the beauty about this is that for the learning part, you only pay the cost of a linear model, but you get the descriptive power of a nonlinear model, namely our ellipse. And the only cost you pay is this transformation. And in fact, if you were to do the inverse transform from the transformed version of your feature space back to the original, once you have your final best hypothesis, this line in this new representation, if you were to sample from it and do a back projection, the inverse function, you're going to get an elliptical shape in the original representation. Okay, and so this transformation on feature space, I did some work here at DSU with a student that deals with some limitations about this transformation. What we found is that this transformation was the same everywhere in feature space. And the research that we did, we said, okay, well, what if instead of transforming feature space, where the chain transformation is applied everywhere, you transform the measurement instrument. And so the measurement instrument is how you measure the difference between the hypothesis output and the ground truth target function. And so we thought, well, maybe if you have a data set where the points are very, very heavily interleaved. And so, for example, let's say you have the plus points here, and there are some positive examples here, and some are closer to the boundary, but let's say most of them are further out like that. And you have some other points, some circles here, and let's say most of them were far away, but some of them were here, interleaved. And so the idea then is that if you make a transformation, it's going to be very hard to separate these points. So why transform everything the same way? Maybe you want this region of feature space to accentuate small differences as if they were large differences. And we call this stretching the ruler, so to speak. And so we developed a framework, and we developed an idea, and actually plays out and works very well, this notion of so-called range transformation. Don't transform the feature space, transform the measurement instrument, and in doing so, you can transform it in a way so that in different regions of feature space, the ruler can be stretched or the ruler can be compressed, so that things that are near to one another in this region, the ruler says, oh, it's a larger distance, but things that are far from each other here, the ruler says it's a smaller distance. And in doing so, the idea is to make it appear as if you're transforming the geometry, and the points that were further away are grouped together, and the points that are interleaved are further apart, like this. And our results play out that this is effective, and we call it range transformation, and we show in this particular publication how you can improve k-means clustering specifically for cases where the classes are interleaved. And that interleaving typically happens near the boundary of the clusters. So it's typically the case you have a scenario that looks like this. You have one set of points here, and you have another set of points here. And what do you do in this boundary region in the middle here, where you typically have the overlap between two categories? Okay, and so that's just a nod, shameless plug, for some research that we've done here at Delaware State that I did not that long ago, a couple years ago, with one of my students. He's now a research scientist in industry. All right, so what this says is that linear models are very good building blocks. We started out with a very simple, seemingly weak, impoverished model, PLA, and it only worked for certain types of data geometries, namely linearly separable data. We said that multiple linear models are good, and we took this linear model and we added a pocket, and we got the anytime behavior. And then we took this linear model and we used the regression solution to bootstrap it, and we saved on the number of rounds we need to find the final best hypothesis. So then we attacked the limitation of this linear model, PLA, where it only performed well, found the final best hypothesis in the cases where the data was linearly separable, and we added this nonlinear transformation, and now we can draw nonlinear decision boundaries even though we pay the cost of a linear model. And so this idea of using linear models as good building blocks, the things that you do to tinker with and change and modify the linear model, give this very simple linear model, seemingly simple linear model, very powerful behaviors. And so we see this through other areas of machine learning. In the case of neural networks, if you take multiple linear models that you compose and you add so-called soft boundaries, nonlinear functions around them, you get neural networks. And this is what neural networks are. They're compositional sums that are passed through nonlinear functions that are weighted by weighted sum, again, through nonlinear functions. And that's a neural network. If you find the boundaries for these linear models in very interesting ways, using the gap between the data points and the boundaries, or the margin, that's called support vector machines, and you can do some very powerful things with them. If you make transformations, like we talked about this phi function, but you can compose these phi functions in a very efficient way where you're not paying the cost of the transformation, that's called a kernel method, which allows you to do some really wonderful things in drawing nonlinear boundaries, but again, you only pay the cost of the linear model. And so we'll see throughout the course of the semester many instances where this seemingly weak, impoverished linear model can do very powerful things just by making certain types of modifications to different places in the anatomy of the learner. So with that, we'll end there, and we'll pick back up on Tuesday as usual. Please stay healthy, stay safe, and I will see you